So protein drug, protein DNA, 2 strands of DNA, whatever it is. So I'm about to populate a picture, a generic depiction of interaction between 2 molecules. What do you think the shape of that curve looks like? Any guesses? I'm seeing a drawing that looks very much like what we've seen before. Okay? So again, there's no actual scale here. But this is showing us, it kind of looks like, I guess, protein plus some small peptide, signaling molecule or hormone coming in and binding. And at some point, again, sort of far away, they have no force. There's no forces in between them. There's no interaction between them. So everything's sort of net zero out here. And then as they get closer and closer and closer, we'll have some sort of minimum distance where it's most energetically favorable. And they're making what type of interactions? What's a type of interaction that these 2 could make with each other? Covalent. What's a covalent bond that they would make? Nope. They're not gonna make an ionic bond. They're not gonna make even a covalent bond except disulfide sulfur-sulfur, potentially. They're gonna make things like H bonds, hydrophobic interactions potentially, salt bridges if they can, all the non-polar electrostatic stuff. And it's gonna look something like this once they get close. Where you can kind of, this is sort of a chain of molecules on big protein. This is sort of part of the little molecule, and you could decompose the interactions that are happening sort of pairwise atomically. And if you wanted to get a total energy of this interaction, you would sum up all the individual interactions that are happening. Okay. So in that picture, where it has molecule A and B and a bunch of lines, where are the covalent bonds and where are the non-covalent bonds? Literally name me the 2 numbers for our different atoms, 1 through 7. So name one of the covalent bonds in like number combo. 1, 2, love it. And 2, 3, and 3, 4. And over here we have 5, 6, and 6, 7 covalent bonds. And all of the interactions are these drawn here. These are possibly, depending on sort of the nature of what these atoms are and what we're dealing with, might be an H bond, an ion pair, a hydrophobic sort of van der Waals style, or like I said, if you had 2 sulfurs coming together, and we haven't looked at the amino acids yet, it could be a covalent disulfide bond. So then, relative to a covalent bond and ionic bond, where do you think this relative energy scale sort of falls, and where do you think the relative distance sort of falls compared to the other things we've looked at so far? So I mean, energetically, do you think probably that this interaction is like deeper, more low energy? And why would you think that? Or not, maybe it's thoughts? There's a couple things coming into play here. So one, we're talking about non-covalent interactions. They're not that strong. So generally, I would say energetically, non-covalent, not as strong as a covalent or an ionic, but I'm also summing a whole bunch of them up at that interface surface. So the answers to almost all my questions can go one way or the other if you defend it to me, right? I think I wrote several true-false last semester that in the homework, it was true-false, pick and explain, and every key was like, it could be either, depending on what they wrote. It's not to trick you, it's just to prove if you know what you're doing, you can explain it to me. Yeah, so it's hard to know. We need more information. Now, distance-wise, I'd probably say it's shifted to a longer distance, that these interactions are happening over a longer range, right? I'm not talking about the actual distance between 2 carbons bonded to each other between their nuclei. That's not the same. That's going to be shorter. This is a bit longer of a range. Okay? And this forms the basis of chapter 12. So that ends the discussion of intermolecular sort of energy. We'll talk about molecular recognition and actual, like, okay, drug and protein binding in much more depth in 12.